Welcome back to AI.Code.Cast. We're going to be tackling a really interesting problem today. It's one of those daily challenge problems, all about finding those sneaky special substrings that are hidden within a larger string.
Yeah, that's right. When we say special, what we're really talking about are those substrings that are made up of the same character repeated over and over again, like uh, or zzz. And, the real challenge here is to figure out the length of the longest special substring, the one that appears at least three times within a given string.
Hmm.
But, oh, and here's the catch, overlaps are totally allowed.
Gotcha. So before we even start thinking about how to solve this thing, I think we need to be super clear on what exactly we're looking for here. Can you toss us an example or two, just to make sure we're on the same page?
Absolutely. So let's just say, for the sake of argument, that our input string is okay.
Okay.
So the longest special substring that shows up at least three times. Well, in this case, it would be And you can kind of see it if you look closely. It's like and you see how those overlaps can really mess things up.
Yep, I'm starting to see it now. So the output, then, for A would be 2. Since the longest repeated special substring, that A, is 2 characters long.
Exactly. You got it.
Okay, cool. Now, what about something a little trickier? Like, what happens if our string is abkaba?
Ooh, good one. All right, so with Abkaba, the longest special substring that we see at least three times is just A. It's kind of hidden in there, but you can find it. Abkaba, and then Abkaba.
Sneaky little A.
Yeah.
So in this case, our output would be 1, because each of those repeating A is just 1 character long.
You got it.
Okay, this is making a lot more sense now. But where do we even begin with actually trying to solve this? I mean, it feels like there could be a ton of potential substrings to check.
Right. And, like with a lot of these coding problems, I think a good place to start, at least when you're just trying to wrap your head around it, is to consider the brute force approach.
Okay.
Now, it might not be, the most elegant solution or the fastest, but it's a good way to lay the groundwork.
Brute force. So we're basically talking about trying out every single possibility.
Yep, that's the gist of it. So in this particular problem, brute force would involve going through and generating every single substring of our input string. Then, for each one of those substrings, we'd have to do two checks. First, we got to see if it's special, meaning it's made up of just one character repeated.
Right.
And then second, if it is special, well, does it show up at least three times in the original string?
Okay, I can see how that would work, but I can also see how it could get really computationally expensive, especially when you start dealing with those super long strings.
Oh, absolutely. The number of possible substrings just explodes as the input string gets longer. That's why we usually don't want to use brute force in a real-world situation. But it is helpful when you're first starting out.
Yeah, it's a good way to get your bearings. So let's imagine we are going with the brute force method. We generate all the substrings, but then how do we check if they're special and if they show up enough times? That seems like it could get messy.
Yeah, for sure. There are a few different ways you could handle that. But I guess one approach would be this. To figure out if a substring is special, you could just go through each character in the substring and make sure they're all the same.
Okay, makes sense.
And then, to count how many times it appears, you could use like a nested loop to compare the substring against every possible position in that original string.
Okay, I can see how that would work.
Yeah.
It's definitely a bit brute forcey, but it gets the job done. Are there any particular pitfalls or edge cases we should be watching out for with this approach?
Oh, yeah, definitely. I think one of the most common mistakes is forgetting to account for empty strings or strings that don't even have any repeating characters. What should our output be in those cases?
That's a good point. I guess if there's no special substring that appears at least 3 times, the most logical output would be, I don't know, minute 1. Like a
I
way of
agree with
saying,
that.
hey, we looked, but we couldn't find anything that fits the criteria.
Exactly. It's always super important to think about those edge cases, to make sure that your solution can handle anything you throw at it.
Totally. So this brute force approach, it's a good foundation, but I'm already kind of itching to explore some more clever and efficient solutions. What's our next alternative going to be?
Okay, so let's dive into a technique that uses hashing. It's really clever and it can really optimize this whole process. You ready to explore the world of hash maps?
You bet. Hashing always sounds so mysterious and powerful. Let's crack this code. Okay, so we've laid the groundwork with that brute force approach, but I'm ready to level up our solution. You mentioned something about using hashing to optimize things. What's the deal with that?
Hashing is such a useful technique, especially when you need to store and retrieve information quickly. And it turns out it can really work wonders with this particular problem. Remember how with brute force we were generating every single substring and then storing them all?
Yeah.
Well, that can use up a lot of space, especially when those strings get really long.
Yeah, I could definitely see that becoming a problem pretty quickly. So how does hashing help us avoid that?
Well, the trick is instead of storing those actual substrings, we can just use a hash map to store a sort of representation of each special substring. We'll just represent them using pairs, the character that makes up the substring, and then its length.
Wait, so instead of storing, like, we would store something like 5.
Exactly, you got it. And you know what? This one little change can save us a ton of space, especially when our strings get really long. And the best part about hash maps is that they let us get to the information that's associated with a key super quickly. In this case, our key would be that character length pair.
Okay, I'm starting to see the magic here. But how do we actually use this hash map to find our answer? You know, the longest special substring that appears at least 3 times?
Okay, so picture this. We're going through our input string, one character at a time. And as we come across consecutive identical characters, what we're doing is basically building up a special substring, right? So then we can calculate its length and store it in our hash map, along with the character that it's made of.
Got it. So if we had something like ABCC, we'd first add AC3 to our hash map,
Yeah.
then B3, and then C3.
Exactly. You're getting it. But there's a bit of a catch. What if we run into the same special substring more than once? Like, what if our string is we
Wow.
wouldn't just want to store 855. You got to keep track of how many times each one of those special substrings appears.
Ah, okay, that makes sense.
Yeah.
So instead of just storing the character and the length, we also need to store, like, a count of how many times we've seen that particular special substring.
Precisely. So our entries in the hash map might look something like 555. This tells us, hey, we've seen all one time and bub one time.
Okay, I'm with you. So we build this hash map as we go through the string, but then how do we actually pull out the answer? You know, the length of that longest special substring that appears at least 3 times. How do we get to that?
Okay, so once we've gone through that whole string and built up our hash map, then all we got to do is go through each of the entries in the hash map. And for each one of those entries, we got to check 2 things. First, we need to know if the count is 3 or more.
Okay.
And second, we check if the length is greater than any length that we've seen so far that also meets that count condition.
Ah, so we're essentially looking for the entry with the biggest length, but only if it shows up at least 3 times.
You got it. It's like we're sifting through a treasure chest. We're only looking for those big gems, and they got to come in groups of 3 or more.
I like that analogy. This hashing solution is definitely way more elegant than the brute force method. But I have a feeling there are even more tricks up our sleeve. What other approaches can we use to tackle this thing?
Oh, we've got some really cool strategies to explore. One of them uses a combination of binary search and a sliding window. Are you ready to dive into that?
Absolutely. Binary search, sliding windows, those sound like pretty powerful tools. Let's see what we can unlock here. Okay, so we've covered brute force, we've talked about hashing, and now you're bringing up binary search and sliding windows. Those sound like completely different approaches. How do they even work together to solve this substring problem?
That's what's so cool about it. When you put them together, binary search and sliding windows make this really elegant and efficient solution. So remember, what we're ultimately trying to find here is the longest special substring that repeats at least 3 times, right?
Right.
And binary search, well, it's perfect for finding the largest value that fits a certain condition.
Okay, so the binary search part helps us zero in on the length of that longest special substring, but where do these sliding windows come in?
Well, think of a sliding window like this. It's a little substring, a fixed length that we're going to move along our main string. And we can adjust the size of this window as we go. For each position of the window, we check if all the characters inside it are the same. If they are, we know we've found a special substring of that length.
Okay, I can kind of picture this window moving along the string. So how do we actually use it with binary search?
Here's where it gets really clever. We use binary search to test out different lengths for our sliding window. We start with a range of possible lengths, from 1, which would be the smallest special substring, up to the length of the whole input string. Binary search keeps dividing this range in half, and it suggests a length to try.
So binary search gives us a length, and we use that to set the size of our sliding window. What happens next?
Well, with the window size set, we start sliding it across the string. If we stumble upon a special substring of that length, and it shows up at least 3 times, then we know we might be able to go even bigger. So, Binary search shifts its focus to the upper half of that range of lengths. But if the window doesn't find a good substring, then binary search knows that the maximum length has got to be smaller, so it looks in the lower half.
That makes sense. So binary search is narrowing down the possibilities for the length, while that slide window is actually checking if a special substring of that length exists and if it pops up enough times. That's a really neat way to combine those two techniques.
It really is. And this approach is way faster than brute force because binary search is really good at eliminating a whole bunch of possibilities with each step. Plus, the sliding window keeps us from doing a bunch of unnecessary checks by efficiently moving across that string.
I'm impressed. Okay, so let's do a quick recap. We talked about brute force, then we moved on to hashing, and now we've explored this clever combo of binary search and sliding windows. That's quite a toolkit. Any other cool approaches from our community solutions that we should mention?
Actually, yeah, there are a few. Some people focused on keeping track of the 3 longest special substrings they found for each character as they went along. Then they just checked if those top 3 met the repetition requirement. It's a smart way to cut down on the search space.
It's amazing to see so many different creative solutions to this problem. I guess it goes to show that there often isn't just one right way to tackle a coding challenge. It's all about picking the best tool for the job, right? And thinking about how efficient you need your code to be.
You got it. If you're only dealing with short strings, a simple approach might be just fine. But when you start working with those really long strings, well, then those optimized techniques like hashing, binary search, or keeping track of those top candidates become way more important if you want things to run smoothly.
It's like choosing the right tool from your toolbox. Sometimes a simple screwdriver is all you need, but sometimes you got to pull out the power drill.
Exactly.
Well, this has been a fantastic deep dive. As we wrap things up here on AI.Code.Cast, what are some of the key takeaways our listeners should keep in mind?
I think one of the most important things is to really make sure you understand the problem inside and out before you even start writing any code. Don't jump the gun. And then second, really think about the pros and cons of the different ways you could solve it. Time and space complexity are definitely important, but don't forget about how readable and maintainable your code is.
Right. No one wants to deal with spaghetti code.
Exactly. And then finally, don't be afraid to play around and experiment. That's one of the most exciting things about algorithms. They're so versatile. When you explore different approaches, you're not just solving the problem in front of you, you're also building up your understanding and your coding skills.
Well said. That's a great note to end on. Thanks for guiding us through this deep dive. It's been a blast.
My pleasure.
And to all our listeners out there, keep those coding skills sharp. We'll see you next time on AI Codecast for another adventure into the world of algorithms.